So as we enter the last, well, 2 weeks really of the class, I have finally posted the 8th problem set of what it's going to be 9 grand total, and I made it due on Friday. Just give you some time to play with it. It's all about lens type stuff and total internal reflection things. So we've covered it at this point. All right. Well, where things left off last time was I did a very quick introduction to the central feature in audio players. And again, audio players, as technology evolves, there was a time when people owned audio players that were just discrete units by themselves. They didn't do cell phone stuff, the iPods of the world. Now your cell phones are effectively your audio players for most of you. And the reason not to change to cell phones is because the emphasis is not on the radio transmission stuff. It's really on the whole idea of how do you have a computer work and how do you work with both digital information and analog information. Why analog? Well, your headphones are analog finally. They're taking a current that's representing sound and turning it into pressure variations that are sound. So it's one physical quantity becoming another physical quantity, or representing another physical quantity. That's the old-fashioned analog world. Anyhow, so my main focus then is to try to give you some idea of how transistors work and then how your computers and audio amplifier type things work based on transistors, and I'll try to keep it succinct. So to set the story again with new batteries in my pointer, a transistor is a more sophisticated semiconductor device, more sophisticated than which one? The diodes. We talked about diodes before as being assembled, at least semiconductor diodes, are assembled out of 2 types of semiconductor. One of them known as N-type, one of them known as P-type. What do the names mean? The N-type material is material that has impurities added to it deliberately that have extra positive charges in the nucleus, and therefore, when they form crystals and try to become electrically neutral, they bring in extra electrons, which have to go somewhere, and they go into the conduction levels of the semiconductor. So this is a piece of N-type material. Over here on the far left, this is N-type material with basically in its pristine glory. It has a full valence band, so nothing can move down here in the valence band, but the conduction band has electrons that can move. So N-type material is an electrical conductor, depending on how much extra, how much you dope it, how much you add these impurities. P-type material, which I don't have up here in a pristine form, P-type material is assembled out, again, in semiconductor, but it has some impurities in it that are short on positive charges, and therefore bring in fewer electrons than are needed to fill out the entire valence band, and they end up with some empty spots in the valence band, which again makes the material a conductor, because it's got some empty seats in a sense in this valence band of electrons. The electrons can use those empty spots to move about and carry electric current. People think of the charge that is moving as a positive charge because it's the empty seat that's so important. It moves around, and the empty seat lacking an electron is effectively positively charged. So people talk about it as a hole moving, a positively charged hole, but I don't care if you remember that. It's just sort of a cute observation. All right, so if you touch P-type material and N-type material, they create a depletion region where they touch. Electrons tumble out of the conduction levels in the N-type material to fill in the valence levels in the P-type material, and you end up with a region that's back to being pure semiconductor-like. It's chemically messed up, but it's effectively like pure semiconductor. It doesn't conduct electricity. If you push charge across it one way, or actually push electrons across it one way, you can get that depletion region to go away and current will flow. And I sort of describe this as water tumbling down a waterfall and continuing on its way. If you try to push current the other way, it doesn't flow. So that's the diode's claim to fame. In this, there are sort of 2 diodes pointing in opposite directions. There's N-type material on both sides, left and right. In the middle is material that was chemically made as P-type material. So when you touched this sandwich together, you get a big depletion region
And it's a hopeless depletion region in the sense that you can't, there's no direction in which you can push current. Because if you try to push charges in from the left, let's say, if you try to push electrons in from the left, just to make so you can follow them, you push them in here, they will go down, they will pile up in here along this depletion region area, but they're never going to make it into the other side, because when you push electrons in from the left, you're also taking them out from the right. You're just going to displace the depletion region, the region that has no electrons in the conduction level, no empties in the valence. Nothing can move. So you'll have this bad spot still, but it will have shifted to the right. And if you try the reverse, you'll shift the depletion region to the left. You can't get rid of it. Not this way. Is this followable, or questions about this? I mean, I can sit here and talk and imagine that you're understanding it and it's all going, but hopefully it's somewhere there. All right? Okay. So this region was chemically made as P-type material, but you can change its character electrically. How do you do that? There's this thing called a gate that is electrically insulated from the transistor's main body. So no charges move between these two, but the gate can have charge on it, and when it does, it develops an electric field. And if you put positive charge on that gate, it's thought of as a metal oxide semiconductor. The gate is the metal. Typically, they actually use semiconductor even there, but they just put so many dopant atoms in that it's indistinguishable from a metal. It carries current like crazy. So whether it's metal or whether it's something that's more complicated that carries current, who cares? The issue is you can put charge on it. No problem. And when you do that, when you put positive charge on that gate, positive charge attracts negative charge. Electrons end up migrating into this region, what used to be the depletion region, and was originally made as P-type material. It effectively becomes N-type material, meaning that it has electrons in its conduction levels. So this is called an N-channel MOSFET, meaning that this is the channel region, the path through which electrons have to move. This is the nuisance of having to go, charge is positive, electrons are negative. It's sad but true. So by putting positive charge on the gate, you turn this depletion, first of all, you get rid of the depletion region, and you turn the central region, the so-called channel, into effectively N-type material. And now the whole thing is N-type material, from left to right. And charge can move either direction. This thing is behaving like an electrically controlled switch. Moments ago, when there was no charge on the gate, no current could flow from left to right, anything, complete, it's just an open circuit. Nothing will go. When you put positive charge on the gate, it's an electrical conductor. It carries current. And I showed you last time, it takes an exquisitely small amount of charge to make this transition. For many MOSFETs, it's a countable number of positive fundamental charges, like protons. 100, 10. It doesn't take many, just a few. There's enough electric field around those positive charges to bring the electrons into the channel and make it conduct. All right? And it's not black or white. If you have no charge on the gate of this, there are many types of MOSFETs. This is an N-channel MOSFET, meaning that the whole thing becomes effectively N-type when you put positive charge on its gate. There's the reverse. There's a P-channel MOSFET, which becomes effectively all P-type when you put negative charge on its gate. And there are various other subtle variations on these things, but this is fine. So you put a little positive charge on this, it suddenly conducts electricity. If you put only half enough to make it really conduct well, it becomes a middling conductor of electric current. So you get the whole gradation from complete insulator to pretty damn good conductor and everything in between. But you choose it by how many charges you put on that gate. And therefore, it shows up not only in digital stuff like computers, which I'll talk about briefly. It shows up in analog things like amplifiers, which are trying to take small electrical signals, make them big ones to drive your speakers or run your headset properly, something like that. It's sort of the workhorse of modern electronics now. And there are, in this room right now, how many are there? There are going to be somewhere, there are going to be trillions of them in this room. Your cell phones, my cell phone has a memory chip in it that's like a quarter of a terabyte or some crazy thing. That's got over 1 trillion MOSFETs in it. So all, they're just everywhere, and they're tiny. They've created ones now, the ones that are involved in a lot of the activity, I'll come to some of the things they do. But they're so small now that really a few charges on them is all it takes, because the whole territory of the MOSFET, it occupies, it's some number, a dozen or 2 dozen billionths of a meter, nanometers on each side. It's just teeny tiny. And a few charges sitting on its little tiny gate are enough to change it from non-conducting to conducting. All right? So examples of what you do with it with these transistors. Let's see. I talked a little bit about the idea digital everything works with symbols. Symbols is just a generic name for the smallest unit that is used to represent information. So a symbol, you're used to symbols. How do you represent a number? A number is an ethereal thing, like the number 16. Ooh, it's some concept that people in any universe would eventually figure out. But how you write it down, if there's a universe where people have 12 fingers on their hands, they're probably going to write it down as a 1 and a 4, because they've got 12 fingers. The 1 represents the 12, that's the 12's place, and then there are 4 left over. How you write it is up to you, and we do write in digital form. We write using symbols. You could also represent 16 as how high my hand is above my other hand. And this is 1, then this is 16. That's pretty clear, right? You can distinguish 16 from 15.9. Nah, right? Not very useful. This is analog representation. Digital representation, the plan is that we work in decimal, which is a base in which numbers are represented in terms of ones, tens, hundreds, thousands, basically the 10 to various powers. And so 16 is represented as the symbol 1 in the tens place, and the symbol 6 in the ones place. And if I do it like this, I go tens place, ones place. It's pretty. I can convey to you that it's 16 very accurately. If I want to do 16.1, and I have to have a tenths place. I can go beyond the decimal point. We can do that. Anyhow, so that's digital and decimal. Digital is the idea of using symbols. Decimal is a choice of bases, and hopefully you've studied bases somewhere in your growing up. I hit math about the time of what was called new math in the 60s, and we all learned bases, base 8, base 2, and all that stuff. And the claim is that the teachers couldn't handle it, the kids could, and so it went back. So that new math came and went. Hopefully you still learned something about bases. We work in base 10. We therefore need 10 symbols to represent everything. We've adopted the so-called Arabic symbols, which don't look anything like the original Arabic symbols that are still in use. We have, that's a 0, a 1, and I can't do a 2, whatever. They look quite different in other countries. But anyway, 10 symbols, that's all you need. And you have 10 symbols that you can use in the ones place, you get 10 symbols you can use in the tens place, 10 symbols you can use in the hundreds place, and so on. I'm thinking of us, hopefully you sometime have heard of Tom Lehrer, who had some good songs about this. Anyhow, base 8 is just like base 10 if you only have 8 fingers. Or or binary is only like the same thing if you only have 2 fingers. Although that can hurt someone's feelings, I gotta be careful. Binary is base 2. So binary is the world where you only have 2 symbols to work with. And therefore, you have to have the 1's place and the 2's place and the 2 squared, 2 to the second power place, which is 4, 8, 16, 32. So representing the number 16 in binary consists of, you use the symbols, there are only 2 of them, so I can make the symbols this, and in the 16's place, this. 8's place, this. 4's place, this. 2's place, this, and 1's place, this. Right? If I were to write it using the symbols that you're much more familiar with, in binary, the number, so it's, woo, the number 16, it's a ghostly thing, okay? It would be written in binary as 1, 0, 0, 0, 0. That's the 1's place, 2's place, 4's place, 8's place, ooh, a 16. That's the 16's place. Can you follow this? Or anybody struggling with, I don't want to admit it, it's hopeless, right? There's no hope. Okay, so point is, you can represent any number you like, and then you can do decimal stuff, it's all there. You can represent any number you like using binary, but you need a lot of symbols. That's okay, they're cheap, make many of them. So your computers these days work with many of the numbers that are working around in your computer are 64 bits long. You might have seen these things on your computer would say, 64-bit processor. That means that the sort of the typical unit that it's throwing around from here to there consists of 64 of these symbols, which can represent an awful lot of detail in the information. So it's no problem having lots of them. You can represent any number you like, and if you want to number things, like all the letters in the alphabet and all the characters that exist, you can represent all the characters the same way. And if you want to do the same thing with words or pictures of the colors, you can work with these binary symbols can represent anything you like. The issue then is how do you work with them to do things that are interesting. So, an example, before showing you an actual implementation of what's called a logic element, let me just describe the concept of a logic element. A logic element is just a conceptual piece that takes in one symbol and it takes in one or more symbols and produces one or more outgoing symbols. And it can do these can be many possibilities, but the simplest possibilities from which it turns out any other possibilities can be produced. The simplest one is what's called an inverter. That's the green guy. It takes in a symbol in binary, which we can call up or down, left, right, 1 or 0. It takes in, let's say 1 or 0 just because it's easy. It takes in a 1 or a 0, and it sends out the reverse symbol, the inverted symbol. So if it gets a 1, it sends out a 0. If it gets a 0, it sends out a 1. You might think, well, that's pretty stupid. But it's actually useful in certain things. Because if you're trying to build more complicated stuff, it turns out you need that guy, that inverter. One input in, one output. The other one is more clever, or sophisticated at least. The blue guy is a not and. And what a not and does is it takes 2 symbols in. And if either one of them or both are zeros, it sends out a 1. But if both of them are 1s, the top one is 1 and, that's the and part, and the bottom one is a 1, it sends out a 0. It basically does a logic and of those two. If you define 1 as true and false, true and false, if you say 1 is true and 0 is false, then when they're both true on the input, it sends out false on the output. With these two guys, and maybe lots of those guys, you can build much more complicated structures. 10 input not and, or something that multiplies 2 binary numbers. You can make a multiplier out of this, or a divider, or an adder, or all kinds of complicated structures. What would a multiplier do? It would take in a binary number represented as the 1's digits, the 2's digits, the 4's, 6, 4's, 8's, 16's, 32's, and so on. Takes in one number, takes in another number just like that. A whole lot of these structures, and out goes a single number that is the one multiplied by the other. They make such devices. And you finally can build any computer you like with a big bunch of these. In a real computer, it's more efficient not to use just these guys. They can build other structures, it turns out, that are faster and more efficient, but that's the basic idea. You just start slamming together lots of these logic elements, and you can sort of make anything you like. Is that okay? And hopefully at some point you studied mathematical logic. For me, it was back in 8th grade, 9th grade, give or take. If A and B, then C, that kind of stuff. These guys just implement it electronically. And to truly implement it electronically, how do you pull that off? How do you make an inverter, for example? So this is an inverter. It consists of 2 Mosfets. They're now no longer drawn out the way I have done up until now. They're drawn using schematic symbols, which you needn't remember. This is the schematic symbol for what is known as a P-channel Mosfet, the one in which, when it has negative charge on its gate, or negative-ish charge, very low charge, then it becomes electrically conducting through a channel that is all P-like. This is the one we met before, the N-channel MOSFET, which when you put positive charge on its gate, it becomes all conducting through an N-type channel. And you put these two together, a P-channel MOSFET and an N-channel MOSFET, and this is a concept known as complementary MOSFETs, and acquired the acronym CMOS, and just almost, everything, almost everything is CMOS these days. So your computers and there's CMOS chips all over the place. You guys are sitting on them, or in your backpacks, or maybe in your hands while you're surfing the web while I'm talking. Whatever. So if you put positive charge on this input, it will go onto both gates. Positive charge going on the gate of the P-channel MOSFET, that's not its favorite flavor. It won't do anything. This will not conduct electricity. So you put positive charge here, this guy doesn't do anything. But this guy does. Positive charge on an N-channel MOSFET makes it conduct. So this becomes electrically conducting, and the output then is electrically connected to 0, to low voltage. So when you put positive charge on the input, you get negative or 0 charge on the output. Whether it's negative or 0 is unimportant detail, but basically, high voltage here, you get low voltage in the output. If you put low voltage on the input, you get high voltage on the output. You turn on this MOSFET. So it does what it was supposed to do. It inverts the input. If we define a 0 as 0 volts here, and we define 1 as 3 volts here, if you put a 1 here, 3 volts, you get 0 volts on the output. That's a 0. They go opposite each other is the only point that matters. And it does it by alternately turning on one transistor and off the other. Would you like me to do that again, slowly? Yes, okay, I'm getting some. So this MOSFET becomes electrically conducting when it has low voltage. Let me talk about presence of positive charge or absence of positive charge, just so I don't keep using too many different random words that are related but not. If you put positive charge on this guy, you turn off this MOSFET. That's not what it wants. It's a P-channel MOSFET. It wants the absence of positive charge to turn on. This guy, being an N-channel MOSFET, the kind that I introduced, the one I talked about at length then, this one turns on when you put positive charge on its gate. So if the input brings in positive charge and puts it on both gates, it turns on this MOSFET and turns off that MOSFET. So only one is on at any given time, which is the complementary concept. They never fight each other, One always gives into the other. So when you put positive charge in the input, the N-channel MOSFET turns on and ensures that there is no positive charge on the output because it's connected to the 0 volt. I should say, these are power supplies. +3 and 0, that's the battery. Or something like the battery, okay? If you take off the positive charge off both gates, so the absence of positive charge, that turns on the P-channel MOSFET. That's what it likes. And this guy conducts, and the N-channel MOSFET, now having no positive charge on its gate, turns off. And suddenly now the output is connected to the 3 volt side of the battery. There's now positive charge in the output. So getting rid of positive charge in the input puts positive charge on the output is the point. It inverts the symbol. Whatever you put on the input, positive charge or absence of positive charge, you get the opposite on the output. Absence of positive charge or positive charge. They go opposite one another. Is that okay? And you can make fancier things. This is the not and. It's got 4. It needs 4 MOSFETs. And it does the same trick, but just it's much more elaborate, of course. And so by the time you get working with the computer chips you have in your gadgets, there will be billions of MOSFETs doing these various complicated manipulations of symbols. Yeah, To? How much charge is needed to transfer 1-bit message? This has been changing with time because the smaller amount of charge they have to move and the smaller the voltage difference they move the charge across, the less power your computer consumes. And at the time I made these drawings, 3 volts was sort of standard what computer chips worked on. I think they're down in the 1 volt range, somewhere in that. They're trying to use the tiniest bits of charge they can possibly move and move it from, ultimately charge ends up moving from the high volt wire to the low volt wire, just like it does in a flashlight filament. And it consumes power. So the smaller the voltage difference between here and here, the less power less energy each charge releases in working its way through the logic gates. And the smaller the charge you need on one of these MOSFETs to turn it on or off, the less charge ultimately is going to be moving from high voltage to low voltage, and the longer your battery lasts. And so I think they're working, in a lot of the logic, they're probably working still with hundreds of fundamental charges, like 100 electrons move from here to there, probably in that range. And they'll try to get down as low as they can. There gets a point where they worry about losing electrons en route, because electrons don't all manage to go through. They'll leak in various ways. But it's basically, they're in the world of countable number of charges, not vast hordes. Is that okay? The memory in your chips, a lot of the memory consists of structures related to this, where as basically the input, they have a capacitor sitting there storing charge. Actually, it may just be the gate itself. If you put positive charge on the gate, its personal MOSFET is, if it's an N-type, is turned on. You put positive charge there, this guy's turned on. You put absence of positive charge there, this guy's turned off. That can act as memory. So if you just have these little gates sitting there storing charge, which makes them essentially capacitors, they can store information. They typically don't store it very long because the charge will leak. This looks all nice and pristine here and clean. There's nowhere to go off in the sides. But in the real world, you're talking about structures that are unbelievably tiny and near each other, and the charges can migrate in ways you didn't expect or want. And they have to monitor the memory and basically keep making sure that it's holding, that it's remembering. There's a kind of memory that you all use all the time too, called flash memory, like the thumb drives. Where's the information on a thumb drive like that? It's stored also on the gates of MOSFETs, but they're what are called floating gates. They're a gate
that is completely surrounded by insulator, which means no charges can get on or off it. It's got an electric field around it if it's got charge, but you can't, how do you get the charge on or off? Well, approximately you can't, and it will sit there for years, trapped in a little world of insulator. It turns out that if you subject it to a strong enough electric field, you can get the charge to migrate through the insulating region, and you can take it on or put it back off. So that's why reading and writing, reading flash is fast, writing flash is slower. It takes a little longer because they have to throw the charge through an insulator, a process that involves quantum mechanics to get it in there. But they do get it in there. But it just, so that will hold its memory for, I don't know, 100 years or something like that. It's just little patches of charge trapped in insulator near Mosfets. Okay? Any questions about sort of digital computer electronics? The last thing, just to give you, I'll do briefly, an analog system. This is an analog amplifier using one N-channel Mosfet. And it's got parts in there that are not worth explaining. But the basic idea is this Mosfet, when it's conducting electricity, tends to drag, to allow charge. This is the output. This is the input. This is the output. There happen to be these things called capacitors on both the input and output for technical reasons. The Mosfet is fighting with a resistor. So a battery, say a 9-volt battery, is allowing positive charge to flow through the resistor and onto this output. If the transistor turns on and becomes conducting, some of that positive charge, instead of going on the output, will go to ground, to 0 volts, and leave. So the more this transistor is turned on, the harder it is for this resistor and 9-volt source of charge to drag the voltage of this output wire up. So the resistor wants the voltage of the output wire to go to 9 volts. The transistor wants it to go to 0 volts, and they fight. And the amount they fight depends on how much charge is sitting on the gate. So as you put tiny amounts of charge on and off the gate of this transistor, the voltage of the output goes up and down. If you make the transistor conduct well, the voltage on the output goes down. If you make the transistor conduct badly, the voltage on the output goes up. And this is the exact circuit I had last week sitting over on the left side of the room, where we had a sound source, a source of an electrical signal representing sound, driving a speaker. This was the power. This was the amplifier for the speaker. And what I showed you with limited success is that the amount of charge that's needed to affect this transistor is so small that I could become part of the circuit and it still worked. So the charge that could flow through me onto the Mosfet's gate was enough to turn the Mosfet up and down and make the speaker make sound. So you have these things in your cell phones. That headphone jack, if it still exists, they come and go, right? The music is typically digital up to a point. They can't send digital information into your headphone. It's got to represent sound, and sound is an analog thing. It's air pressure, continuous fluctuations in air pressure. So one of the last things they do is they take these numbers that are representing air pressure, a whole series of numbers, air pressure measurements, one after the next, at tiny intervals of time, and they turn those into a single current, a fluctuating current. Now it's analog. So it's a digital to analog converter. And once it's analog, they go through an amplifier to have enough power in that analog signal to actually create the sound, which involves power. Fluctuations of air pressure aren't free. They carry energy. They carry, yeah. So they go through an analog amplifier. So your cell phone it's about 95% digital, but there are a few analog pieces to it. The speaker is certainly analog. The microphone is also analog. All right? Any questions about electronics, cell phone type, stereos? I don't even know. Do you even talk about stereos anymore? Everybody's computer is the stereo. All right. With that, then, I'm going to leave I'll leave electronics and go to something completely different. Ha-ha. Oddly relevant. Yeah, any demonstrations? Yes, you do have demonstrations, although not actually, not going to blow anything up too bad. You know, I don't even want to joke about making a phone call to North Korea. I didn't say anything. Now I'll probably be monitored by the NSA or somebody or other. All right. So I'll ask, is it possible to have 100 tons of plutonium not have it explode? How many think yes? How many think no? Okay, you're all going for yes, which is right. It's a question of where you distribute the stuff. So if you have 100 tons of plutonium, you don't want it all in a small location. For good reason, we'll see why proximity matters. And okay, so here's the story then. You know, obviously they release enormous amounts of energy. The hottest things we know how to make. They produce radioactive fallout, which is worth talking about a bit. And fortunately, they're relatively difficult to make. Alas, not difficult enough. And they use what are known as chain reactions, where one event triggers a subsequent event and triggers a subsequent and so on. And that's ultimately why you don't want a whole lot of plutonium in the same small location. All right, so some questions to go after. First off is, in fact, what is nuclear energy? Where is it stored in the atoms? And we'll go from there. So, first question is, where is it stored? And the answer is that it's stored in the nucleus of the atom. So I've talked pretty vaguely about atomic structure. We've seen that the periphery of an atom is its electrons. Unlike how you learned way back when, they're not little planetary things, those electrons. They live as standing waves around a central positive core. So they're attracted to this positively charged core. You typically, in a normal atom, it accumulates enough electrons to exactly reach neutrality. So if there are 37 fundamental positive charges on that core, it will attract 37 electrons. And that 37 electrons will go into these standing waves, i.e. orbitals, and that determines the destiny of the atom. That will tell you everything about its chemistry. The electrons are determined chemistry, and the number of electrons is determined by how many positive charges there are in that core. All right? So, what's the core? The core is, first of all, it's fantastically dense. That is, it's got an enormous mass per volume. It's, lengthwise, it's about 100,000 times smaller than the overall diameter of its diameter is like 100,000th the diameter of the atom itself. So how big is an atom? A typical atom is on the order of 1/10 of a billionth of a meter. So a tenth of a nanometer, pretty small. But to find the nucleus, so 10 to the minus 10 meters. The nucleus is typically on the order of 10 to the minus 15 nanometers. The shorthand name for that, not 10 to the minus 15 nanometers, 10 to the minus 15 meters. And the name for a billionth of a meter is a nanometer. The name for a trillionth of a meter is a picometer. And the name for 10 to the minus 15 meters is just called a Fermi. So the nuclei are measured in Fermi. One neutron or one proton is about a Fermi in diameter. You have to, if you get a bunch of them together, they get a little bit bigger. They are also quantum mechanical thingies, and therefore they have wave character to them too. It's easier to think of them as little balls, but that's not accurate. And there are people in this department who study this and would, I'm sure they're very aware and interested in the wave-like character of these little pieces that make up the nucleus. Okay, so they're really tiny. They have the vast majority of the atom's mass. So a proton weighs has a mass about 2,000 times that of an electron. So if you have the same number of protons as electrons,
you have 2,000 times as much mass just in the protons living in the nucleus. It's just got a lot of mass. Electrons are trivial for mass. So that's true of anything you have at home. You know, it's this flashlight, all but 0.01% of the mass of this flashlight is in the nuclei of the flashlight, not in its electrons. There's this famous equation, E equals mc squared. You know, what is that? That comes out of the Einstein's special relativity, the observation finally that well, it ties up space and time are kind of more interrelated than you might think, and that interrelates momentum and energy more than you think. And it also, when you start looking at the relationships that give you kinetic energy in old-fashioned Newtonian physics, it turns out that even at zero velocity, objects retain an energy. If you watch the object's energy increase as it goes faster and faster, something we do in Newtonian physics that I've taught you already, if you shift over into the world of relativity, that's still happening. You go faster and faster, you got more and more kinetic energy. But if you go down and come to a dead stop, the energy doesn't go to zero. It goes to a starting point. And the starting point turns out to be the object's mass times the speed of light squared. The speed of light being this special speed in this universe. It's named after light because it is, but it has, even if light didn't exist, that speed of light would still be an interesting speed. So it's special. Anyhow, it's very fast, and therefore if you take an ordinary measure of mass, like a kilogram, and you multiply it by the speed of light squared, you get an enormous quantity. It happens to have units energy because it is an energy, and the point is that if you could, which is not trivial to do, if you could turn a kilogram of mass into energy, redesignated as energy, it would be a lot of energy. It would be 9 times 10 to the 16 joules. It's just, whoa, a lot of energy. And that means that even if you can turn a small amount of mass into energy, there's a lot of energy there. And where's the mass? It's in the nucleus. So look to the nucleus for the most energy around. All right, so what does a nucleus sort of look like? And this now I'm ignoring quantum mechanics and I'm drawing a nucleus as little balls. But this is a typical sodium nucleus drawn with I got protons red and neutrons blue. A proton is a common subatomic particle. There are only 3 really common subatomic particles in our world. Electrons, we already met them. Protons are these little things, a lot of mass compared to the electron, and they're positively charged. They carry 1 positive fundamental charge, and they live in nuclei. The nucleus of a hydrogen atom is a proton and nothing else. That's the normal hydrogen atom. Diluting the protons are neutrons. Neutrons are very much like protons with one exception. They have no charge. So hence the word neutron. They're neutral. They are kept together once they touch by a force that I've never talked about in this class, which is, it's known as the nuclear force. It's actually related to a more fundamental force known as the strong force. But it involves the quarks and gluons. I'm not going to go there, but basically it's a short-range force, unlike the ones we've encountered up until this point. Gravity and electromagnetic forces go on forever. You're affected in principle by the gravity of the distant stars, and you're similarly attracted. The positive charges in you are being affected and attracted by the negative charges off on Pluto. So there's no limits to the distance in that case. But the nuclear force falls off very quickly as you get outside of a proton or neutron, which collectively incidentally are called nucleons because they're the wherewithal for making nuclei. So nucleons stick when they touch, or they experience a very intense attractive force. The strong force is always attractive, never repulsive.
So if you think about what's going on in that sodium nucleus, it's actually got two major forces going on here. One of them is that contact force that I just talked about, the nuclear force. They want to stick together because on contact, it's like Velcro, they grab. However, there are 11 protons, each carrying one positive fundamental charge. They're repelling each other, and they are really close. So that repulsion, at least relatively speaking, is quite strong. They would love to get apart, but the nuclear force wins. In this case, the repulsion of the protons is intense, but the nuclear force is stronger. It holds that sodium nucleus together forever. So once you've made the thing, if you don't come and smack it with something and break it deliberately, it's going to be there forever. But there's a competition between a repulsive force, that is the electrostatic repulsion of the protons, and the nuclear force, the attraction of those nucleons on contact. Okay? Well, the sodium nucleus is happy. Yeah, it's worth asking this way. If you snip the nucleus of a very massive atom, suppose you make an atom that has, just to pick at a random number, 92 protons. If you snip that baby in half, it would release energy. Where was the energy stored in? And you get two choices, the electrostatic repulsion between the protons or the nuclear attraction between the nucleons. You okay with the question? How many think the energy that was released when you snip that thing in half and let it fly off was electrostatic repulsion between the protons? How many think it was the nuclear attraction between the nucleons? Okay, well let's assemble this guy from two halves and watch the process. So we've got the two halves, each of which has half 92, which is 46. We snip. Anyway. I'm pushing them together. This is hard. I'm having to push them together as they move together. I'm doing work on them. What am I pushing against? They're at great distance still. It's the electrostatic repulsion, right? I'm pushing charged thingies together. They hate it. Don't do it. So they're accumulating electrostatic potential energy. The voltage is going up. And then they touch. And in that last minute of touching, the nuclear force pulls in and does work back on them and on me. Ooh, that last little bit, I got a little bit of work done on me. I got some energy out. And that energy came from nuclear force, nuclear potential energy, I guess. Right. I was pushing them together. They're getting harder and harder. I was storing energy, and the last little bit, they released energy because they stuck and they pulled together that last little bit. Instead of me pushing them together, they pulled together that last little bit and stuck. So the answer to this is actually A. It's a repulsion of the protons. They hate being so near each other. The nuclear force holds them together because in order to get them apart, you have to pull them enough apart to get them to stop sticking. So if you invest a little energy by you do work to break them a little farther apart, then they can get going and off they go forever. So the energy that's released when a giant nucleus blows apart, like 92 protons, that's uranium. When uranium breaks into two halves and flies off like that, the energy that's coming out is actually electrostatic potential energy. It was stored in there when the nucleus was made, which was a star explosion in the distant past, 4.5 billion years ago, give or take. Everything from which we are made of was produced in an exploding star. And in the explosion, things got stuck together that should never have been made. And that included uranium. Who needs a nucleus that big? It wouldn't normally assemble, but the violence of the explosion was enough to assemble these too many charges. They stuck, and they're there. And they are now coming apart all the time. And an example, so I might as well show you something. This is VistaWare, orange VistaWare. This is just a shard. Orange is expensive. If you go looking
go to eBay. The other colors from these are from the 1920s or 30s or something. The other colors are relatively inexpensive. Not orange, because the orange glaze, they used uranium as part of the pigment, as a color. That's uranium orange. Isn't that lovely? And the uranium nuclei in there have so much energy stored in their electrostatic potential energy that nuclear force is only barely able to keep them together. And for interesting reasons that I'll have to do next time, they come apart occasionally. And when they do, they're exploding. This is detecting the shrapnel that's coming out when those nuclei blow apart. So they made radioactive dinnerware. It was great. All right, so we'll do more. We'll do more on to Wednesday. You can come look for radioactive stuff if you want.